Good evening all. We'll wait for a couple of minutes and then get started. If you have any questions before starting with my questions, we can discuss them first. Yeah, I guess I was disconnected. So we'll get started. So this week the lectures discuss on why do we need nonlinear activation functions and some aspects related to initialization of the weights for neural networks, and then it gets started on recurrent neural networks, subsequently discusses GRU and LSTM, and finally concludes with bidirectional RNNs. So we'll go through a couple of things that are necessary for you to solve your assignments. So the first question here is why do we need nonlinear activation functions? I've just taken an example of a sigmoid function that you have here. It follows in this particular pattern. So if this is a neural network and if my activation function in each of the neurons is a sigmoid or say tan h, whichever one of these nonlinear functions, then what is usually expected from this is if you observe the pattern here, only if the values are within a certain range, only if the values are within a certain range, the sigmoid function will have certain value, certain gradient, and beyond this particular point, the one in this particular zone as well as in this particular zone, it kinds of reaches a saturation. It kinds of reaches a saturation, and then the gradient becomes 0, and then the further it won't be learning anything new. So this is a kind of a filter. So for all the values in this range and for all the values in this range, the sigmoid function reaches a particular constant value. So this can be treated as a filter that kind of suppresses all inputs below a level. So if this is your neural network, if these are my inputs, only certain connections will get activated to reach the final output. So this could be one possible way. You can also have something like this. Or you can have something like this. The ones that are highlighted are the neurons that are activated. By actually seeing these different patterns will correspond to different kinds of scenarios of the input combinations that will give you a particular kind of output. This is achieved only because of this nonlinearity, where it is able to differentiate between a certain value of the input features. Say this threshold and this threshold. This is something that is common for all the nonlinear activation functions. Now the question here asks you about ReLU. ReLU is a rectified linear unit, where you have if this is my input, so you have a linear output for x greater than 0, and then for x less than 0 is a constant. So you can write ReLU as ReLU of x is essentially maximum of 0 comma x, or you can write it as x for x greater than or equal to 0, and x less than 0 it will be equal to 0. This is my ReLU function. So is this function linear or non-linear? Is linear. Okay, so to answer that question, so what kind of functions do you consider as linear? So if you have a functional form something like y equal to mx plus c, if it is of this particular form, you call this a linear function. Now ReLU is essentially y equals max of 0 comma x. So what is the value of m and c that will give you this particular function, or maybe I'll write it as this: x and 0 if x is greater than or equal to 0 and x is less than 0. So can you tell me the values of m and c that will give you this particular function? If you have some finite values of, if you have some values for m and c that can give you this this particular form, then you consider that function to be linear. Could you come up with the value of m and c? For a you wouldn't be able to capture that because the functional form is essentially something like this. So in this region it will be linear, in this region it will be linear, but however at x equal to 0 you have some discontinuity, so you will not be able to get a single value of m and c that will satisfy the entire equation. So it is not essentially a linear function over the entire domain. This is some important feature that we were discussing again. So whatever function, activation function you will be using, it needs to have this particular kind of a feature where it can act as a filter. Essentially it needs to allow only certain values of input and should prevent other inputs to flow to the output. That way it will ensure that certain patterns will actually form inside, and only with each specific pattern, say if only these particular set of neurons are getting activated, you get one kind of output. Say if you have something like this getting activated, then you have a different kind of output. For things like that to happen, you need to have this nonlinearity. ReLU has that nonlinearity because it differentiates between x less than 0 and x greater than 0. This is one important feature of that. And even if you consider other activation functions like tanh or leaky ReLU or any of the functions that you can consider, it will have the same features. So let us say, let me give you one another function. This is say a soft sine function. It goes something like y equals to x by 1 plus mod x. This is if you plot this thing, so this can be written as if I plot this, if x is positive, this value is going to be half, and if x is negative, this is going to be this won't be defined. So even though this has that discontinuity, but you have other difficulties with this. Say if I use some constant alpha here, so alpha is something that is less than 1, so I'll have some value here and some value here. So this has a discontinuity here, so it you can kind of differentiate here as well. So for positive values of x you have a definite constant value, and for negative values of x you have another constant value. Can I use this function? It is definitely not linear. This is a nonlinear function because I cannot get unique values of m and c that will be satisfied over the entire range. So can I use this function in my neural network? Is the question clear? So we discussed one point is it should have this nonlinearity, which it already has. It is nonlinear function because you cannot just get unique values of m and c. So this is nonlinear. So can I use this function as an activation function? Maybe let's say we'll just stick with this function. No, gradient will be 0. Yes, if you try to calculate the gradients in the gradient of this, since it is just a linear, in this particular region it is a linear, in this region, so the gradients will be 0. So if gradients will be 0, you won't be able to learn anything. So this cannot be used. Though it is a nonlinear function, you cannot use it because its gradient is 0. Okay. So the second question, consider say you have a logistic sigmoid function, or say any you have a single layer perceptron or any neural network, and the layer output is given by this, where g is a nonlinear any nonlinear function. It can be one of these four. W is the weight vector, H is your hidden state from the previous layer, and B is your bias. And say initially while you were training it, it so happened that you have given very low values of W, or for instance, consider an instance where this initially the model is learning only the values of B so that it can fit all the input with the corresponding output. Such a scenario, what could happen is it will learn only the values of B to match the input with the output, and then it will see it will make the WH equal to 0, where H can actually tend to 0. Essentially all the hidden layer outputs will be going to 0. In such a scenario, which of these activation functions would you prefer for a deep neural network? What I was trying to say is, say you have an input x, and then it goes through several hidden layers, h1, h2, so on, h6, and finally you are getting an output by hat. Now what we are saying, at any of these intermediate layers, you have the output of that intermediate layer as wh plus b, where h is the hidden layer of the previous layer. So in this way, what could happen is, while it was fitting, it is learning only the values of bias, so that it could actually make this equal to 0. Now wh equal to 0 implies either w can be like, you can have either a very low values of your weights, something like this, or it could also because of your hidden units are actually tending to 0. That could also happen. So if we consider the second scenario, that is h is tending to 0, so all the previous layers are actually getting 0 values. So this is a scenario that you are facing, like you have developed a network, you have fixed one of these activation functions, and then you are observing this, and you want to change your activation function. So you have say initially you started with sigmoid and you ended up with this problem, or will you end up with this problem if you start with sigmoid or tan h or LO or Leakey LO? Which of these? Okay, first of all, why is there any problem here? So the network is only learning the values of bias instead of weights, by essentially making h equal to 0. Yes, there is a problem. That is the problem. Okay, so what do we do now? Is this problem you are not learning anything? It will act as a shallow network. So if all the hidden layers are 0, what could happen is only the outer layers will get trained and all your inner layers are actually becoming 0. So you will not learn anything. So where do you think the problem is? Is the problem with the sigmoid? Like which of these will give you this problem, or all of them will actually give you the problem? Okay, let me kind of put it slightly differently. So say this is I'm saying you that this is only, yes, like you said, it is only problem with sigmoid. So why is it the problem only with sigmoid and not tan h? Maybe others can try to answer it. So Saran is pointing out that this scenario arises only with sigmoid and not with the other activation functions. Okay. So okay, the problem is there with sigmoid, that is understood. I think it okay. So let us answer first, elaborate on what Saran was trying to say. So why is this a problem with sigmoid? So if you happen to see the sigmoid function, if there is no input from the hidden layer, so what will happen is something that we discussed in the last week as well. So you have this saturation problem, where a 0 value of sigmoid is this region where your sigmoid will actually become 0. So h is basically the output from the previous layer. So if h is tending to 0, it means all the previous layers, the values of sigmoids are extremely large, so that the value is becoming 0, h is becoming 0. So in this way, in this particular region, your gradient becomes 0. So all those layers will not be able to learn anything further, and that is why you are getting stuck there in sigmoid. So why do you think tan h doesn't have this problem? So if you were to plot tan h function, it's similar to sigmoid, the only difference is it will be offset. So it will be something like this. So this is tan h. So here, if you observe, if the values are tending to 0 in tan h, you will still be in this particular region, in this region where gradient is not zero. So even if you get stuck because the gradient is non-zero, you can still come out of that situations in tan h. So it's better to use tan h. The same logic, if you apply the same logic for ReLU, so what would happen? So what about the gradient or gradient at 0 for ReLU? If it is a positive, you will have a finite value and still you should be able to get out of it. The same happens with leaky ReLU. Leaky ReLU is essentially similar to ReLU, just that in ReLU you have 0 and something like this. In leaky ReLU you will have you will also allow a certain amount of value even for negative values of x. That's the only difference between ReLU and linear ReLU. So the important point here is the functions for which the gradient is not equal to 0 at 0 values of input. This is another feature that we expect in some activation functions for certain kind of scenarios. What we are trying to say here is by choosing something like this, you will be able to accelerate your convergence. It doesn't mean that it will always converge to a solution. Sometimes it will actually be better than using the other functions like sigmoid. Okay, now let us ask another question. So can we initialize all the weights to the same constant value? If say I am using say sigmoid or any of these functions, if I use any of these functions, can I initialize all the weights to be the same value? Say 0, I initialized all the weights to 0 and start my training. Can I do that? Of course I can do that. So will it actually converge to a better solution than doing any other initialization? So why is this question relevant here? Is because this is a scenario where you have WH tend to 0. So all of this is for the case where H is tending to 0. An alternate scenario can arise where W could actually tend to 0 instead of H tending to 0. Even in that scenario, you won't be learning anything. So that could happen when you are initializing small, of course, random values. So why do we have to use random values? Can't we just say initialize all the weights to be zeros? Yes or no? First we'll split it into part by parts and then we'll see. Can we initialize all the weights to be 0? And still be able to get a better solution? Yes, no, not sure. It will be a sparse scenario. Okay, can you elaborate on what you meant by sparse scenario? So like ideally the value of weight could be any number. I'm just saying I will initialize all of them to be zeros. So if you have an optimization problem, all I'm doing here is changing my initial condition. So like initial, whatever initialization I'm doing, the initial point I'm starting with, that is the only thing I'm changing. And I'm using the, say suppose we'll use the steepest gradient descent. So if this is my optimizer, so all I'm doing is I'm changing the initial guess for the optimizer. So instead of giving a random initialization, I am saying I'll initialize all the weights to 0. So what do you think the problem would be? or maybe, okay, first let's discuss with zeros and then we'll go a little further. So if all the weights are 0, what would happen is, say if you have a network like this, the initial one, so if you have a network like this and all these weights are 0, so nothing will actually pass from input to output in the initial stage. And when you calculate gradient, all are actually giving the same values. So the gradient will be symmetric in all directions. So it will flow equally in all the directions, and then again it will split equally in all the directions, and then this keeps going on, so that it wouldn't be able to get the differentiation feature easily. Only after certainly very large number of epochs, it can actually go to something. And to actually prevent these things, we are actually giving some random initializations to some of these weights, some value other than 0. Even if you give, let us say, instead of zeros, to some constant value, any constant value, say 1, all the weights have initialized to 1. Again, you will have the same problem. If all the weights are 1, so every neuron is kind of equivalent to every other neuron. So the gradients will actually flow equally in all the directions, so it wouldn't be able to differentiate between different kinds of inputs. So then it wouldn't be able to get the functional form properly immediately. In order to increase the chances of this optimization better, what we do is do some random initialization. Okay, is this point clear? Yeah, I guess there are no questions, so this is clear. So if this is clear, we'll get to the next question, where that is something that we are discussing, that has been discussed in this week. So now we understood that all the weights cannot be the same value, so there should be some kind of difference between them in order to ensure that it will be able to capture different kinds of relations among the inputs. So which of these following would you expect for the gradient terms to be? Say if you calculate from one layer to another layer, so whatever these weights are there, whenever you are calculating gradients and then you are flowing them back, which of these properties would you expect for these gradients to have, for the mean of the gradients and variance for them? Out of these 4 options, which one do you think? Okay, first of all, is the question clear? Okay, so what I was trying to say is, if this is my output and then the gradients are actually flowing in this direction, so if I see the value of gradients in this particular weights, so if I calculate the mean of these gradients and variance of these, which of these would I expect the values to be? Or what is an ideal scenario or a better scenario for my optimization algorithm? Which of these scenarios will actually be good for my optimization, so that it will converge faster and maybe converge to a global instead of a local minima? Which one of these will increase the chances of something like that? Okay, so I hope you have already gone through the lecture videos. So it discusses something on Xavier initialization. Since there is an assignment question on this, I am not going to go in depth for Xavier initialization, but I would like to highlight only a couple of points. So why are we going with this? Like we have discussed previously, like it shouldn't have all zeros or all constants, because that would actually give like it will introduce additional symmetry into the network, so that gradients will flow equally in all the directions and it wouldn't be able to differentiate different kinds of inputs. So if that is a scenario, then we decided that we will actually give some random initialization. So now the question now that comes is, if it is a random, like we discussed in our earlier classes, there are different kinds of distributions from which you can generate your random numbers. So what is that particular distribution that you are going to use now? Say if you are going to use Gaussian distribution, we have discussed some, like you can use uniform distribution, Gaussian distribution, and then we have Bernoulli, binomial, different kinds of distributions. Say if I am using Gaussian distribution. So if you are using Gaussian distribution, it will be parameterized with only 2 quantities. your mean and your variance, or mean and your standard deviation sigma. So if mu and sigma are given, then you should be able to get these weights as random. So now the question that needs to be asked is, what should be the values of this? So in order to answer this, we need to understand what is the expected value of these gradients that are flowing back in order to ensure that your optimization is happening in a proper direction. So what is it? Say suppose if this is my layer 1, this is my layer 2 and layer 3, and this is my output. Say here if you have a mean value of say 2 or something, and then here the mean value after getting multiplied with all of this will actually increase, and if it again gets multiplied, it could actually increase, and this keeps on increasing. So if your depth is actually a little higher, so this mean, if it is a very high value, it will actually keep on increasing, which could actually lead to something like your exploding gradients. Or consider reverse scenario where your weights are, say it is 0.8, and then it gets multiplied with all the weights, and then it gets reduced to 0.6, and then it reduced to 0.2, and eventually this, if this keeps going on, your mean will actually go to 0, and then anything below that will actually do not learn anything. So this is your vanishing gradient problem. So you shouldn't have very too low value, at the same time you shouldn't have very too high value. But usually what is preferred is, say if you have mean equal to 0, so you don't have anything that is keeps on exploding, so you can prevent this exploding by actually having mean equal to 0. But at the same time, if all the networks like we have discussed here, so if every direction is equivalent to every other direction, then the network would not learn anything. So you need to have some kind of asymmetry in this. This is something that could be introduced by your variance term. So if you have a very high variance here, then it will learn, actually each of these neurons will be fully utilized to capture a different aspect of the input. So you need to have a variance that is not equal to 0, and if mean equal to 0, in that particular scenario, you are actually preventing exploding gradients. At the same time, because of the variance, you will have some differences within these gradients, so that each neuron will be able to learn each different aspect of the input feature. So you need to have something like this is actually preferred. So if you have both of them to be not equal to 0, so a very high value of mean and variance could actually lead to exploding gradient problem. If mean is not equal to 0 and variance equal to 0, in that particular scenario what could happen? In this scenario what could happen is, because variance is 0, all the weights are equal, all neurons will be symmetric. So 4 neurons are being used to essentially learn one feature, which is actually not good, and the optimizer will not converge to a global optima. And if both are equal to 0, then again the network will not be able to learn anything, because still as long as variance is 0, that symmetry cannot be broken, and then it will not be able to learn anything, any new features easily. Is this clear? Of course, the question now is what should be the value of this variance, and what should value of mean is 0. So what should be the value of this variance to ensure that you prevent this vanishing gradient problem? That is a different question that will not answer here, but people who are interested can actually look at the paper for this Xavier initialization, and then you will be able to answer those questions as well, which is again out of scope, so we will not be discussing that in this session. There are no questions. I think we'll go to the next one. After this, the lecture videos discuss something on RNNs, so recurrent neural network. So the idea here is you have a time series data where you have a sequence of data, something like x0, x1, xt minus 1 to xt, and then you pass this as an input, and then you get output y1 to yt. So this can also be seen as like if you kind of open it and unravel it, this can also be seen as your regular deep neural network where you have several layers. The only difference between that and this here is the weights that you are using here is kind of shared weights, like your CNN, similar to your CNN. These are shared weights. So The equations here shown are for a vanilla RNN, where you have your H is your hidden state from the previous time step, and then you will be using that as well as the new input value to actually calculate the next hidden state, and with the hidden state you actually calculate Y. So what are these W, U and V? These are the weights that are being shared across different layers. So this is a simple RNN, but now if you see the problem that is also be discussed here is if you try to apply backpropagation to this, so this particular weight, say if you want to calculate gradient of this particular weight, it will get contribution from, say if you are having at say layer 5. For fifth layer you will have H5, and H5 is related to H4 plus, and H4 is again related to H3, and so on. So when you calculate these errors, so error, say if I am using mean square error as my, so it will go something like minus y5 actual whole square, and if I want to calculate del j del w, so this has terms from all of this. So it will have a term from y5, the first error term, and then it will have a contribution from h5, 4, 3, 2, 1. So at any time step, if you want to calculate the error, it will include the errors from all the previous time step. So for yt, it will have from yt minus 1 so on till y1, and again similarly for y2, it will have from y2, it will have from y1. So this way it will the gradient information has, the error information has to flow across this entire network and reach the final one. Like what we have discussed previously, like if you are using sigmoid function, it could actually have some saturations, and after a certain point, when all of these neurons are saturated, the gradient will actually be 0 and it wouldn't actually propagate this long. So this is something that we are calling that it has a certain length of memory. So it will only be able to understand say 3 or 4 layers, usually 5 layers, sigmoid can go up to 5 layers. So beyond 5 layers, the gradient will actually vanish, and then if you use, if you have an input series length of 10, you cannot use it directly because of this problem. So this is already discussed in lecture video. So before going to next question, yeah, we'll come to LSTM for this. So the point I would like to highlight here is the concept of why the gradient vanishes is clear. Second, how a recurrent neural network can actually be expanded into a deep neural network, and how can this actually help us in understanding the vanishing gradient problem. These two are the points that I would like to highlight here. We'll come to the question whether LSTM will actually solve this. To answer that question, maybe I can take this as an initiation. So now this is something that we have faced even in CNNs. So if you recollect, in CNNs we also have this problem. So we were developing deep networks even in CNNs. So when you have a very deep network, there also you are having this vanishing gradient problem. So how did we solve that in CNNs, say for image classification problem? Skip connections, yes. So in we introduced skip connections, where essentially you have say if this is my layer 1, layer 2, layer 3. So if this was the usual flow from input to output and gradient is vanishing, so what we introduced there is something called skip connections, so that your gradient can actually So we have provided some pathways so that your gradient information can actually go to the neurons directly. So this is something that we have done in CNNs. Similar idea will be used here. So I've just listed down all the 3 different kind of architectures here side by side, so that it will be easy to compare. So this is a vanilla RNN. So and then comes the GRU and then LSTM. So we'll keep GRU aside for a second, and then we'll discuss GRU first, or LSTM. GRU can actually be expressed as simplified form of LSTM, so we'll discuss LSTM directly. So LSTM also introduces something very similar to your skip connection. So what it does is provides another layer here, so something called a cell memory, which actually stores these values and provides a way for your gradient to flow, which was not there in your vanilla RNN. So in vanilla RNN it has to actually flow all the way here. So however here we are providing this path as an alternate one. So your gradient information can actually flow in this path. Otherwise it has to actually flow through all of this. In addition to these connections, we are also providing this additional path through which your gradient can actually flow. That way we are kind of ensuring that your gradient will not actually completely vanish. So mathematically, so what we are trying to do, ht is the hidden state at t time step. We are using an output gate that will decide what features should be used to decide how much of the input information can actually flow to the output, and this information is stored in the cell state. C is called the cell state, or you can call cell memory. And then how do you update the value of this cell state? You take the previous cell state value and then you have something that is taking inputs from the current input state as well as the previous hidden state. Using these two informations, you will decide how much to forget from the previous state and how much of the new information should you use. IT is the input gate that will decide how much of the new information you should be using. FT is a forget gate that will decide how much of the information that is present in the previous memory that should not be used in this current connection. So that is your that is how you update the cell state. C bar is actually the update from the current input and the previous time step. I again is your input gate. Input gate is again depends on your input and your previous hidden states. So it's very similar to your vanilla RNN in this only this particular part. The only difference between LSTM or GRU in addition to vanilla RNN is you have some gates that will actually decide how to update your next hidden state. If you observe here we are just using previous hidden state and input value to update the value of HT, and from HT we will use another transformation V to actually get YT. In GRU what we were doing, we take the previous value, we take the current update, so this is the updated value from the current one, which uses again previous hidden state and input to get this value, and we decide how much of this information to actually go to the next state. F decides the fraction of the from the previous time step, and G decides the value that is actually going from the current input state xt. So this is how you update this. Once you update this, you can actually from HT you can calculate YT using some similar transformation. In LSTM, in addition to forget gate, we are adding two more gates, which is an input gate and an output gate. This input gate will again depend on your xt and HT, so that will decide how much of the input should actually be used to decide the cell memory. And the same time forget gate will decide how much of the information present in the previous cell should actually be used to update the current cell value. So now this is about the gates. So now coming back to the question, so how does this actually help in preventing the vanishing gradient? Is essentially because of introduction of this particular value, the cell state. So these cell states only have quite a few operations. So this is something that is so if you see in vanilla RNN, the YT, the actual output depends directly on your HT. So what happens here is HT will again depend on HT minus 1, and from HT minus 1 you have to go to H2 minus 2 and so on, and after a certain point the gradient will actually vanish. But here however, CT minus 1 is an explicitly stored value which will not vanish. So if you since the value is actually stored in the cell that could actually be directly used, this value will not vanish directly. C bar is something again that depends on xt, HT minus 1, and HT minus 1 will again depend on HT minus 2, and this will keep going on. But however, presence of this value will actually store a value in CT that will not vanish. I think, is this clear, or maybe I need to elaborate a little? Okay, maybe I need to elaborate a little. Is this clear, or do I need to elaborate a little? A little. Okay. So it's like this. So you have, so let's expand this. So you have x0, x1, x2, so on xt, these are my inputs, and then you have this, and there is some kind of information here. So H0, X1 will go, and then this will decide what is the next output layer. This is what we were doing in a vanilla RNN. So this will keep going on, and finally you will reach HT minus 1 and HT. So what we are doing here in LSTM is we are providing additional values for each of these cells. So these values will actually store how much of the information to be used in actually predicting the value of H1. So in addition to X1, you are now using, so if you see how the value of HT is calculated, HT now includes the output as well as OT is again dependent on XT, HT minus 1 and CT. So in it now we have 3 inputs. So in order to decide H1, I am using X1, H0 and C1. This C1 is only dependent on C0. All of these weights are connected. So now you have, when you calculate the gradient with respect to H1 weights, or when you calculate gradients with respect to X0, so the information will flow, instead of going through this way, now it will only go through C0, C1, only this particular network. So this was the way before, and this was the way now. So if at any other layer if you see, so it will actually go only in this particular value. So now it is a linear one. So instead of having a deep network where you have going in different ones, now you have one kind of kind of a conveyor belt kind of thing, where all the information is stored in certain values and you are accessing from this. Even here you will have the same problem. Say even if the cell states are too high, so if you have 100 cell states, then as you move from say if you are at C100 and you want to go to C0, then you will still get the same problem. When you want to go from C100 to C0, after passing 100 layers, the gradient will actually vanish in LSTM as well. The only thing that we are saying here is by using LSTM we are able to mitigate the problem, because previously it was from H1 to X0 you have one nonlinear, and X1 to again H0 you will have another nonlinear. So instead of these different complicated path, we have eliminated it with a single path, C0 to C1. This will only kind of reduce the problem, but still the vanishing gradient problem can exist in LSTM as well, especially when you have a very long sequence and you have very long value of this particular sequence, because now the gradient is flowing in this direction, and if the length of this is very long, you will still have the vanishing gradient problem. So it won't solve the problem completely, it will only kind of reduce the problem, because it provided a kind of a simpler path for the gradient to flow. Is this clear? Okay. Now let us so say suppose you are not using bias, like none of these equations has bias. So like we were doing this in CNNs, so how many parameters are there for a given kind of network? So the question was not asked in assignments right now, but maybe I thought I will discuss this as well. So how many parameters are actually present in each of these architectures? So okay, now you understood that LSTM is kind of a little better than GRU, or say better than RNN, because it kind of reduces the vanishing gradient problem by providing an alternate path. The question now is at what cost? What is the additional cost that you are facing in LSTM in order to gain this additional advantage? How many parameters do you have to actually learn for this architecture to work? Say in vanilla RNN, so let us take here. So what are the learnable parameters in this vanilla RNN? Yes, in vanilla RNN you just have 3 parameters that you have to learn, and those are your W, U and V. These are the matrices depending on the network you are using. So if you are using a neural network, you can use any network of your choice. This decides the matrix will depend on the network you have chosen. So these are the three parameters that you have to learn. So basically you have three matrices. So in GRU, how many matrices you would be having? Sorry. Six. So you have WZ, UG. These are for the output, and then you need to learn your forget gate, for which you need WF, UF. So what are the other two matrices? Okay, I think you might have included bias as well. Okay, like I started out with the assumption that there are no bias, so otherwise you would have some bias terms as well, which we will not consider for now, just for simplicity. So if you ignore the bias terms, you will have to learn your forget gate, for which you need two matrices, and you'll have to learn your normal output one that you have G. G is like the output of a plain vanilla RNA. So we have two here and then two here. And then again, I think you might have included the output as well. So when you want output, YT will again depend on your G times V of HT. So this will add one more parameter, so which is something that I am excluding now. So in further architecture and the equations I have shown, you have just 4 parameters to learn. So now coming to LSTM, so how many would you think it has? Okay, by now it is kind of straightforward. So you have to just sum up all of these. So you have an input gate, for which you have two parameters, two matrices, and then you have an output gate, again for which you have two matrices, and then you have a forget gate. Input and output gate decides how much of the input should go to the cell state and how much of the output should actually be sent to the next hidden state. Forget gate will decide how much of the previous cell state to actually use here. This is where forget gate is being used. So here again you need two parameters. So you have 3 gates and then you have 6 matrices here. And if you include the final output, then you have one more additional matrix, which I am not included in the model that I have shown here. So you have 6. So compared to plain vanilla RNN, now you are having approximately 3 times more number of parameters in LSTM. So this is kind of memory intensive, and you would also actually, since the number of parameter increased, you would have to actually use more training data to actually train this particular model. Okay. So before actually going to the next question, so how many of you are already familiar with attention? Okay, then maybe I should skip that part. Okay, let us consider another question. This is the final question for this week. So say you have a chemical reaction that is happening and you want to predict the evolution of temperature for that particular reaction, and you want to model this problem using a bidirectional RNN. Can I use it directly or not? A simple question, yes or no, and why? So how is it bi-RNN different from others? In a normal RNN, you will be just using information in one direction. So here what we were doing is, when you want to predict the hidden state of H1, you will be just using X0 and X1. In bi-RNN, what we will be doing is, we will also use information from the other neurons to actually predict the value of H1. So this way, it is actually useful in some of the text processing, where you need to get the context for a particular word. You might have to look at both the words that are occurring prior to it and something that is occurring post of that particular word. So this is something that where bi-RNN is actually being used. Now I want to put it in a different application. Say I want to use bioRNN for this particular application where I have some chemical reaction. I want to predict the temperature of that particular reaction, the temperature of that particular chamber in which the reaction is happening. Can I use a bioRNN to model it? So what would be my training data set? Say I have T and temperature. So I have different time steps and I have temperatures for each of these values, and this is my training data set, and I want to predict the, like I'll give my time instant and then I want my model to actually predict, say at a given instant I'll give some history of temperature and then it should actually predict me what the temperature would be in the next time steps. I want my bioRNN to be trained on this. So can I use this directly or do I have to make any modifications? If we need correction in our output, then we need bioRNN. Correction, okay. What do you mean by correction? Okay, let me means changing output when new data arrives. Okay, so basically what is my training data set is I'll have different instances. Say suppose t equal to 0 to say 10, I have 10 different values. I'd say whatever time step I have certain temperature values, and then I take another sequence say from 0.1 to 10.1, and I have another sequence from say 11.0 to say 21.0, and then I have a sequence from 12.9 to say 22.9. Like this I have different sequences. So for each sequence it needs to predict say a certain values of outputs. So if I give from 0 to 10, it should be able to predict say from 11 or 10.1 to say it will predict maybe 20 steps ahead or 10 steps ahead. So if my input is from 0 to 10 seconds, it should be able to predict the next 10 time steps. So like 10.1 to say 20.1. If it is from 0.1 to 10.1, it should be able to predict from 10.2 to say 20.2. So something like this. So if this is my input, I expect this to be my output, and I am training my model on this. So the question now is, can I use a bioRNN to train a model? Like, can I use bioRNN as a model for this kind of data? Of course, once I train this, I'll test on a different data. Then obviously my input, say suppose if this is my training data, and my testing data would be on a different time instance. Say I have not used here say 0.5 to maybe 10.5. This is something that is not present in my training data, so I'll use this as my testing case, and then I would like to predict from 10.6 to 20.6. So this should be my output. This is the testing set. So can I use a bioRNN in this particular scenario? Okay, you don't think bioRNN is needed? Okay, any other viewpoints? Anyone says that we can use bioRNN? Okay, let us say, okay, let us not answer the question is bioRNN needed or not. Maybe the question is not clear. So what I was trying to ask is, can we actually use bioRNN to model this? Can we use or can we not? It is needed or not is something different. So can we use this problem? Can we model this using bioRNN or not? Like in sequence prediction, what we were doing, like if you want to understand the context of a word, you need to look behind and after the particular word. But in some physical models, especially when you have time series like this, what it means is you have to look at the past and future of that particular time instant to actually predict something in the future. In this scenario, it is quite simple. All you're doing is just looking at the past and then you are predicting something. But then if you expand this model, so all you're doing is t equal to 0 to t equal to 10. You're using all the past information to predict your future information, so 10.1 to 20.1. So this is kind of casual in nature, so we can just use all the past information and then predict something that is happening in the future. So this is something where you can use a bi-RNN that could actually give you better results than a simple RNN. Because if you use a simple RNN, what would happen is, say it is from 0 to 10, 0.1 and so on. What would happen is, when you want to, 0 will be used to predict 10.1 and 0.1 will predict, like to predict 10, the value at 10.2, it will use both 0 and 0.1. And similarly for predicting the last value, which is at 20.1, it will use all the values. It will use 0, 0.1, 10. All of this will be used to actually predict this in a simple RNN. But now if you use a bidirectional RNN, what would happen is, in order to predict this 10.1, it will not only use 0, it will also use all other values. So it will use the entire history to actually predict this. Is the idea clear? Okay, I think it's more clear. So what I'm trying to say is, okay, it's clear. Okay, let me put the question slightly differently now. So instead of predicting next time step, now say if I have my input data something like this. Say I am using my input as 0 to 10 and that is predicting something 0.1 to say 10.1, say 0.2, like it is just predicting one step ahead. If this is my input and output, so can I use bi-RNN for this as well? It's like I have this as my timing, correspondingly I have my temperature as well. This is my output. So basically my input is temperature values from time 0 to 10, and then I am using that information to predict the temperature from 0.1 to 10.1. Similarly from 0.1, these are different training instances that I trained my model on. So can I use bi-RNN for this particular scenario? Yes? Anyone who says no? Okay, I got one answer saying yes. So any other alternate viewpoints? Yes, you can use bi-RNN. Okay. Okay. So let us see. So what we are doing here, if you use a bi-RNN, like as we discussed, so if you are using bi-RNN, it will see both input from both the directions in order to predict a particular value of the output. So when you want to predict the output value at 0.1 second, you are actually using information from 0 to 10, all time instances. So to predict the value of 0.1, you are using at 0, 0.1, 0.2 and 10, which is something you wouldn't expect in any physical model, right? So if you want to find the temperature at instant t equal to 1 second, you can only use the information between 0 to 1 second. You cannot use some information about the future and then predict from it. That is something that cannot happen in reality, right? So even if your model can actually give you good results, but then it is not a casual model. This is different from the previous scenario. So if you happen to see in the previous scenario, what we were doing there is you are using input from 0 to 10 seconds to predict the values of output at 10.1, 10.2 and 20.1. So there, even if you use this connection from both the directions, there you are just using the past information to predict something in the future, which is something that can happen. You are just using the time history to actually predict something that is going to happen in the future. But if you use a bi-RNN in this particular scenario, what is going to happen is you are, in order to predict something here, you are actually using future information which is not actually available to you. So if I want to predict at 0.2, I should only use values from 0, 0.0, 0.1 and 0.2. I should not use all these values upstream. That would be unphysical. You can still develop a model that could give you an accurate result, but the model will not generalize better. So it might work very well on your training data set, but when you go with a new data set, it might not actually work because these things will not generalize better. In this scenario, bi-RNN could not actually generalize better. Is this clear? In summary, if we have some past and future values, then we can use bi-RNN value. In summary, if we have past and future values, then we can use bi-RNN. Yeah, just to put it in summary, if you want to use bi-RNN, all you need to ensure is your output, when you are predicting a value of a given output, it should only use the past values. That is for the scenario when you are using time as your input. This is not the case in the typical way where bi-RNN has actually been introduced. Bi-RNN is introduced for language translation tasks. There it doesn't matter whether you go this way or that way. It needs to actually look in both directions to get the context of the word, so it was useful there. But for physical models, if you are in some of the physical domains, if you are doing CFD or some other problems, bi-RNN should be used only if your output is completely future and your input is completely past. Yes. I think we have covered all the problems related to assignment. So you have any other questions you want me to discuss? Or you have any other specific queries? These are the questions I have for today, and I think I kind of addressed all the problems discussed in the assignments. BPDT static GTX bidirectional analysis. Any other queries? Can LSTM be used for asset price prediction? I mean, it's kind of a very generic question. Okay. Yeah, that I understand, but it depends on the data you use and things like that. So, if can be used or not is thing. Like you can use LSTM for it. You can use LSTM, that's the only thing I can say, but I cannot tell you whether it's the best model that to use, or because after LSTM there are several other architectures that are introduced. Or maybe we can elaborate a little on that. What is done after LSTM? Transformer, yes. I think transformer will be discussed in subsequent weeks, so maybe we will take that up when it is discussed in the lecture videos. You can actually use a transformer. It is shown that transformer can actually be trained in much faster using GPU than an LSTM. The main reason being in LSTM, if you see here, or any of these RNNs, if you want to predict, like when you want to calculate your gradients, you are actually looping through entire thing. So if your sequence length is larger, for each training step you have to actually go through all of this in a for loop. So that for loop is where you have more time spent. So that is kind of removed in your transformer. You don't have this for loop there. So what transformer does, I'm not going exactly in it, but the idea here is, here you have these shared weights. So what if I can replace this entire thing with a single neural network that has this as my inputs and then these as my outputs. Okay, first let us ask that question and then we'll go to attention a little later. So the question now is, say instead of using this RNN network, can I directly use this as my input and this as my hidden layers, and then that will be my output. I can just replace this entire thing with a neural network. Can I do that? Of course, the question is very similar to what we were discussing in CNNs. So even in a CNN can actually replace with a fully connected neural network. The only problem there would be a CNN is very sparse in nature. So the number of weights required is actually much lower in a CNN. The same idea comes here as well. So in RNN, the number of weights required is actually much lower than if you were using a fully connected network. Why is the weight matrix need to be constant throughout the time or sequence? If weight matrix is constant, how information time or sequence is preserved? Okay. So why the weight matrix need to be constant? So say suppose you are having a physical model. Say any of these different, even for the case he has mentioned. So can LSTM be used for asset price prediction? So what are the typical models you will be using in asset price prediction? I'm not actually from finance background, or I'm from mechanical background, so I'm not sure about what they do in that. So but for most of the physical problems, say you have a simple scenario, something like this: d square y by dt square is essentially something like minus c, say a freely falling object. So if this is a governing equation, every time step will actually follow this. So if you consider in time, if you use a simple discretization for this, it will be something like y at time t will actually, you can directly solve this. So this is the solution you will be getting. Yt is minus, it's actually falling. So let's say the origin is at somewhere on the top. So minus half gt square. So this is the solution you have. So if you are modeling, if you want to remove this t and you want to kind of predict the relation between yt and yt minus 1, so what would be the relation? Plus something. So I will write this as yt is a function of yt minus 1 and so on, yt minus 2 and so on. This functional form will actually depend on the physics of the problem. It is not going to depend on anything else. So this is the idea that we are using in RNN. So across time steps, we want this functional form to remain the similar so that it follows the same physics. So all we are doing is parameterizing this functional form with a neural network of some theta comma whatever is here. So that is the reason we are using the same matrix everywhere. Next, so is the first part clear? So as long as this differential equation remains the same, you want the weights to be same across the different layers. If weights are different, then it means that your governing equation itself is kind of changing from one time step to another time step, which is something that we don't want. So what we are trying to find in an RNN is that simplified governing equation that satisfies the, that is kind of preserved for all the time sequence. If that is not the scenario for your problem, then RNN is not good for your problem. Is the first part clear? Yes. Now coming to your next part. If weight matrix is constant, how information from the previous time or sequence is preserved? It's not actually preserved. So yeah, again, so I think this answers the first. So as long as you understand that the weight matrix here is used to parameterize your differential equation, or for the fundamental part that is kind of preserved across the time step. So what you are doing here is, once you know that this is a form, this is the kind of evolution that this process has to go through, all it changes is by changing the input values, your output will actually be different. You don't have to store anything. So it's like, to put it simply, I can give you a simple example where, if you are familiar with the Euler form of it, so if you have a simple differential equation dy dt equal to some f of t, so what you would be doing is yt plus 1 is essentially yt plus f of t times whatever delta t is there. So what we were trying to do is, this is the functional form here. I can write this as f of, or maybe g of yt and so on. So all we are doing is, by fixing, when the neural networks learns the weights will essentially store how to actually process these inputs to get the output. So the way you are doing this should be same across different time steps. Your weight matrix is constant in that sense. It is not like your weights are actually constant throughout your values or something. It's just that it is preserved, like you want the same operations to be happening for any values of your input sequences. Your weight matrix is a constant. I think I kind of explained your question, or did I or did I not? Maybe you need to actually tell me, like, is it clear or you have anything? Yeah, it's clear. Any other queries? Maybe I should point out, like here, one more point. Like in RNNs, like similar to CNNs, even in CNN you are doing the same thing. So you're having the shared weights across it. So can I use CNN in place of an RNN? So what, say this is my input x0, x1 and so on, xt. I can directly use a kernel. Say I'll fix a kernel of some fixed size and then use this, and from this I'll predict some outputs. Can I do something like that? Maybe can I replace even in CNN you have this shared weights concept. The idea there is also very similar. So the weights there, like you kind of fixed what the kernel operation is, and then you decide this weight. So the weights will decide how to process your input in different stages. So that is something that has to be shared across the image. So all we are doing here now is we are removing the image and then we're keeping it time series data. So essentially, instead of image, now you have a long length of like one sequence. So can I do that? So I can call this a 1D CNN. Feed forward will okay. Feed forward is possible with CNN. Okay, by feed forward you mean to say the fully connected network or something? All of these networks can be replaced with a fully connected network, that is for sure. The only problem is if you can solve the problem with just 50 parameters, but then you are actually having a model with 100 parameters. How to preserve spatial info if you replace CNN by RNN? Okay, the question is actually the reverse of it. We'll get to your question again. The question now that I'm trying to ask is, can I replace a RNN with a CNN, not the other way around? So instead of RNN, can I use a CNN in this particular scenario? I have my input sequence. I take a kernel, this, and do whatever we are doing in CNN, and finally get an output sequence. So like if you, yeah. So if you happen to see here, it's like saying that is what you are like. All we are doing here is having these several networks where each of them is actually sharing the weights. All I am asking you now is, can I use a kernel to actually do this? Maybe the weights you get could be different, but the idea is same. Like that's one we have discussed before. when one of the questions was asked. So it's very similar. All you want here is you need to have some shared weights. That is something that CNN is also satisfying. So I can use CNN as well, right? Yes or no? Okay, maybe I can give you a little hint. So there was one question previous week, I think he didn't join now. Yeah, but so if you are using CNN, so what does your kernel size signify? The kernel size will actually determine how much of the input is actually used to predict it. So what is what to call that? So if I were to replace this RNN with a CNN, what should be my kernel size? If I use a short kernel like this, what would happen is it will only use these two values, or as the kernel progresses it will only use two values. But when to predict the value of a given output, to predict this particular value, it will only use these values, only use two input states. But if I am using an RNN, it is actually using all these particular values to actually predict this. Like if you are using a bi-RNN, for example, if you use a very simple RNN to predict Y0, it will only use this. To predict YT, it will of course use all of this. Let us say we are using a bi-RNN. So if you use bi-RNN to predict this, it will actually use the entire sequence to predict this particular value. But a CNN will only use partial ones. So in order to replace this RNN completely with a CNN, you need to have a very large kernel. And we have discussed like kernel, you have to do a lot of matrix multiplications in order to do this convolution operation. So that would be computationally more intensive. So even RNN is computation intensive because you have to actually loop through each of these stages and then predict these values. So both of these are kind of intensive. So one is doing a for loop, the other one is doing matrix multiplications. So even in matrix multiplications, you have three different for loops that you have to kind of do to actually get a particular output. So both are kind of intensive, but theoretically you could actually replace an RNN with a CNN. So, and you can find most of the literature where people have found good results even with CNN on some of the time series data. Extension to this is where you use attention mechanism, or maybe like transformer uses something called attention. That is something that okay, I do not want to discuss on that, but you can go through it. We can discuss it once it is discussed in the lecture videos, after it is discussed in the lecture videos. Any other questions or queries, or is this clear? These are the questions I have for this week. If you do not have any further questions, maybe feel free to leave. If you have any questions, we can discuss them. Thank you. Then I think there are no questions, and yeah, we'll end the session for today. Thank you all for joining.